You know that feeling, right? Your car breaks down, you're stranded on the side of the road, and all you can think is, I wish I'd known this was going to happen. Well, what if your car could have told you? That's exactly the kind of technology we're diving into today, the future of self-diagnosing systems.
I mean, seriously. Just imagine a power plant that sees a critical failure coming and prevents a massive blackout. Or what about a huge office building where the climate system just fixes itself to save energy before anyone even feels a change in temperature? This isn't science fiction anymore. This is the real promise of a technology that's quietly changing how we maintain, well, pretty much everything.
For the longest time, we've lived in this totally reactive world. Something breaks, we scramble to fix it. It's a model that guarantees higher costs and, let's be honest, super frustrating downtime. But the big shift now is toward predictive maintenance. It's a whole new game where we use data to fix things before they ever get a chance to fail. We're talking about less downtime, smarter use of resources, and, at the end of the day, a much more reliable world.
And the engine making all of this happen is called fault detection and diagnostics, or FDD for short. Think of it like this. You have a ton of sensors collecting data all the time. And then you have these incredibly smart algorithms, usually machine learning, that are constantly sifting through that data, looking for the earliest warning signs of trouble.
Okay, so this proactive revolution sounds great in theory, but what does it actually mean in the real world? How does it change things on the ground? Because this is so much more than a cool gadget, it's a fundamental change in how our systems operate.
The benefits are just huge. In a big building, for example, FTD can tweak the heating and AC systems to slash energy waste. By catching a small problem early, you're not just avoiding an expensive emergency repair down the road, you're actually making the equipment last longer. The result? Safer buildings, way better efficiency, and some serious cost savings.
All of this, the savings, the safety, it all really boils down to one fascinating question. How does a machine even know that something is wrong with itself? I mean, it sounds a little bit like magic, but it's actually based on a really clever engineering principle.
And that principle is called analytical redundancy. Okay, I know, that sounds super complicated, but the core idea is surprisingly simple. Instead of physically putting 3 sensors on one part to double-check a reading, which is pricey, you can use math to create virtual sensors that constantly check up on the real ones.
So here's the key. You create this perfect digital blueprint, a mathematical model, of exactly how a system is supposed to be running. Then, in real time, you feed it data from the actual system. The second the reality starts to drift away from that perfect model, even by a little bit, bam! The system knows a fault is starting to develop. It's like having a ghost in the machine that's constantly looking over its shoulder, making sure the work is getting done right.
And this is where things get really exciting. Because to analyze all this data and figure out what's actually going on, we are now teaching machines to think like expert mechanics, and we're doing it using the power of artificial intelligence.
Now, to get a handle on the toolkit, it helps to know the lingo. Think of AI as the huge overall concept of intelligent machines. Inside that, you have machine learning, which is where we teach computers by just showing them tons of data. And then you have deep learning, which is like a supercharged version of machine learning that uses these complex brain-like structures to find patterns that are way too deep for us to see.
So, with that framework in mind, let's take a quick tour of a few of the most popular AI tools that act as the brains behind FDD.
First up, you've got something called K-nearest neighbor, or KNN. The easiest way to think about this is diagnosis by committee. Let's say you get a weird vibration reading from a motor. KNN looks at the handful of closest data points it already knows about. If most of its neighbors are labeled bearing failure, then it's a pretty safe bet that this new data point is also a bearing failure. It's simple, but it's a great first step for classifying known problems.
Next is the support vector machine, or SVM. An SVM is all about drawing the sharpest possible line in the sand. Its whole goal is to create the biggest possible gap between two groups of data, like, say, all the data points from a healthy system versus a faulty one. By making that dividing line or margin as wide as possible, it gets incredibly good at classifying new info. It's perfect when you need a clear, confident yes or no answer.
And then you have the heavy hitters, artificial neural networks. These are literally inspired by the human brain. They use layers upon layers of these digital neurons that all work together to spot incredibly subtle and complex patterns in the data. Patterns a person or even a simpler algorithm would totally miss. This is the kind of power you need to diagnose those really tricky faults where a bunch of different factors are all tangled together.
So why do you hear the term deep learning so much? Well, if you only have a little bit of data, those other methods work just fine. But in the real world today, we have absolutely massive data sets. And the magic of deep learning is that the more data you throw at it, the smarter it gets. Its performance doesn't just level off, it keeps getting better and better, pulling way ahead of the pack.
Now, of course, as powerful as this all is, it's not some magic bullet. Trying to implement these systems in the real world comes with a whole new set of challenges that folks are working hard to solve right now. Putting this stuff into practice is tough. First and foremost, you've got data quality. The old saying, garbage in, garbage out, is basically the golden rule of AI. Then there's the headache of trying to get your shiny new AI to work with some 20-year-old piece of equipment. You also have this weird problem where faults are, thankfully, pretty rare, which makes it hard for the AI to get enough bad examples to learn from. And maybe most importantly, these super powerful models can sometimes be a complete black box. They give you an answer, but you have no idea why. And that black box problem brings us to one of the biggest frontiers in this field, explainable AI, or XAI. To really trust these systems, especially when the stakes are high, we need them to do more than just give us an answer. We need them to show their work. Building that trust, that interpretability, is absolutely essential for this technology to really take off.
So after our quick tour through this whole world of diagnostics, let's step back for a second. What's the big picture takeaway here?
The main thing to remember is that we are in the middle of this massive shift. We are moving away from a world of surprise breakdowns and emergency repairs, and we're building a smarter, more resilient one. A world powered by systems that can watch over themselves, diagnose their own problems, and even predict the future, making everything run better. And that really leaves us with one final thought to chew on. Our machines, our buildings, our entire world is getting more and more complex every single day. Are we reaching a point where these intelligent diagnostic systems aren't just a nice-to-have, but an absolute necessity to keep the whole thing from falling apart? It's definitely something to think about.